In this video, I want to talk about angular momentum. So first, let's define angular momentum for a particle. For a single particle, the angular momentum is given by an expression that, just like torque, by itself doesn't say much until we know what these mean. So P is the momentum, the linear momentum of the particle. Linear. And R takes the place like the R from the definition of torque. It is defined relative to an axis. So the first thing this implies is that we must have an axis about which we can evaluate the angular momentum. And once we have that, then R points from the axis to the location of particle. So, with our understanding of what R and P means, we can have angular momentum. So, we can define it and we can calculate it. So, does a particle moving in a straight line, some linear velocity v, have angular momentum? It can, certainly. If we define an axis, say here, we can evaluate an r vector that points from the axis of rotation to the place where the particle is. And then, let's give some values here. Let's say we have a, let's give ourselves a coordinate system. Let's say that's plus x, plus y is up, and that puts plus z out of the screen. And so let's say we have a velocity here equal to 30 meters per second and be a positive I hat. Now, if it's immediately sort of up relative to the origin, so if we say our origin is the origin of our coordinate system, and the r vector points purely along the y-axis, and let's say it has a distance of 5 meters. Okay, and so r is equal to 5 meters j hat. We're going to say our particle has a mass of 1/2 kilogram. We can then calculate our angular momentum. So L, which is r cross p, is in the magnitude of r, magnitude of p, magnitude of our momentum. Sine theta, where theta is the angle between r and the momentum when they're tail to tail. And then n hat is a unit vector determined by the right-hand rule, perpendicular to both r and p. So the magnitude of r was 5. The magnitude of p, which is m times v, the m is 1/2, v was 30, and then we need a unit vector. All right, so if I do the r cross p, so p is pointing in the same direction as v, of course. So if I do my right-hand rule, index finger along r, middle finger along p, my thumb points into the screen. So given my choice of coordinate system, then my unit vector will be along the negative z direction or negative k hat. So our angular momentum, 1/2 of 30 is 15, times 5, so it'd be negative 75 k hat, and it'll have units then of kilograms, meters squared per second. All right, is that great? So meters per second times the kilograms times meters. Okay, so there's the angular momentum of a particle, in this case moving in a straight line that happened to be, where its momentum was perpendicular to the radius vector at that point, so we could calculate it about this location. Obviously, if we were to choose a point along the line, along the path of the straight line trajectory of the particle, then the angular momentum would be 0 about that point, because r and the momentum vector would be parallel or anti-parallel everywhere. All right, well, let's take a look at a particle moving around in a circle then. So I have now, well, I'm not sure that was a very good circle, but okay, so I have here a particle, and it's moving at some velocity v at this instant around the circle. Well, we know from before that the r vector from the center of the rotation to the particle is always perpendicular to the tangential velocity, or the velocity. And so the angular momentum is fairly straightforward to calculate in this case. Magnitude of r, magnitude of linear momentum, sine theta. Theta in this case is always 90, wherever it is on the circle. And so this is then r, then mass times velocity v. And in this case, if we have plus x plus y, as z is out of the page, if I do r cross v, the right-hand rule, my unit vector gives me a positive k, give me along the positive z-axis. All right, so let's look at the magnitude of my angular momentum L, which is r times m times v. So if we multiply the top and the bottom, top and the bottom, we multiply it by r over r, we can rewrite this as m r squared times v over r. And this is the angular velocity omega. So that gives us m r squared omega. But remember that this we called the moment of inertia I for a single particle. So thus we can rewrite the angular momentum, magnitude at the moment, is equal to the moment of inertia of the particle times the angular velocity of the particle. Now, this relationship holds for an extended object rotating in a plane, as long as we can define our moment of inertia about an axis, then the angular momentum about that same axis is equal to that moment of inertia times the angular velocity rotating around that axis. All right, so let's just do a quick example for that. We'll come down here. So imagine I have sort of a merry-go-round here that's a 100 kilogram uniform disc, has a radius of 2 meters. Now I have a person out, let's say 3/4 of the way. We have a 40 kilogram person, and they're at a location 1.5 meters from the center. Okay, and let's just say this whole thing is rotating around with an angular velocity of a 1/2 radians per second. Okay, so what is the angular momentum of this entire system? Well, our angular momentum then is going to be the moment of inertia times the angular velocity. So the moment of inertia now is the sum of the moment of inertia of the disk plus the moment of inertia of the person. And so we have to calculate each one separately. We'll assume that the person is a point particle at this location on the disk. So our angular momentum then is equal to the moment of inertia of a uniform disk is 1/2 mass of the disk, 100 times the radius of the disk squared. And the moment of inertia of the person, we're assuming is a point particle, is mass times their distance from the axis squared, which is 3/2 squared. And this is all times the angular velocity, then, which is 1/2. Okay, so if I look at this looks like 200 to me, and this is 9/4, so 90 times 1/2, so 290 divided by 2 looks like 145 kilograms meters squared per second. It's a magnitude of our angular momentum. So if we look at the vector, then we note that, again, this is for rotations in a plane of a single rigid object. And in that case, then the angular momentum is pointing in the same direction as the angular velocity. So we use our right-hand rule to determine the orientation of the angular velocity, which for a rotation that's given in the picture, that would be up. And so our angular momentum would then also be pointing in that direction. If, for example, we called y, say, positive y up for some reason, then that would be the angular momentum would be in the y-axis. If we called, say, z up, so xy would be in the plane of the rotation and positive z would be up, then it'd point along the positive z-axis. And so the main thing here is to point out is that as long as for a continuous object here, rigid object rotating in a plane, where you can define a moment of inertia about a singular axis, then the angular momentum is pointing in the same direction, is oriented in the same direction as the angular velocity.